My name is Oguzcan Karagoz, but it's really hard to pronounce, so you can tell me the O's in principle. Today, I would like to talk about the mapping of contractional structures and a little bit related landforms due to the time limit. Let's start quickly. What is this contractional landforms? We can mainly know them as a resultant in the stress, and the main types of them is in the wrinkle ridges and the lobate scarps. And you should keep on your mind always what we are dealing with the planetary geology is always a descriptive terminology, like what we are seeing and what we are describing. And both of them is actually relatively similar, but they have some differences in their formation and also in the appearance. Okay, let's start with the wrinkle ridges. Wrinkle ridges are the positive relief landforms. We are looking to landforms like the mountain belts, but in relatively small scales. And in the right, we can see in the CTX image, I hope you follow the first day and today early talks about different data types and different process for this planetary imageries. This is a CTX data from the Mars. They can be, the wrinkles can be linear to asymmetric appearance or sometimes sinuses, sometimes they can discontinuous. And if you're familiar with the term, it's called echelon array. They can be also an echelon array. Their heights could be hundreds of meters high, and they can be hundreds of the kilometers wide, developed under compressional regime. Okay, these wrinkle ridges can be found in all of the planetary bodies, all of the terrestrial bodies. They can be in different forms, like a ring belt form in the Mercury, let's say in the left-hand part, and the Moon, they are more straight, roughly, and they have some in the Mars, the echelon arrays, like they're following each other, the structures. But what about the lobate scarps? Why we are just distinguishing them and characterizing in the two different segments? The lobate scarp means actually, again, the positive relief structure, but their appearance is mostly linear. We can see them in the linear appearance on the top view from satellite imagery. They're also very high and higher offset and vertical throw than the wrinkle ridges. And if you look them, they have steeper thrust. And their main characters is the flattening hanging wall in the behind of that. So let's look here in a very simple example, and which I really like. We have one wrinkle ridge and one lobate scarp transition. The wrinkle ridge, we can see the boundary of the ridges, like here. And I just noted that with the red line, you can follow them. And the lobate scarp, we have basically like a table mountain and a flattened hanging wall appearance. They can be seen in the Moon and also in the Mars, as I said. Okay, but what caused this compression, this deformation actually? I summarize here for you. We can see all impact cratering, like all terrestrial planets and the planetary bodies. And by feeling this impact cratering, we should start from the beginning. Like we have a crater and we feel that the crater with the recently occurred lava, and this lava is creating the loads on the lithosphere and start the bending and the cooling afterwards. This cooling effect of the basins of the flat basalts creates and form these wrinkle ridges, and they mainly appear in the ring shape, like in the Mercury in the previous one. And also the planet itself can be cool down and shrink, which can see that phenomenon in Mercury and the Moon very frequently. And the tidal forces like Earth-Moon example or Io example, we can see some accumulation of this lava, and it also create like lithospheric horizontal stresses. And another one, which I involve highly, the plume-induced horizontal shortening. We can imagine like you have a volcano, the Hawaii, you're creating the lava and the volcanic product, and that's coming up to the lithosphere, and your lithosphere is deflecting, I mean the bending inwards. And this volcanic product in the top of the lithosphere is starting the sliding effect. That creates a horizontal shortening. And all of them occur on the float basalt units. Okay. In principle, the wrinkle ridges or lobate scarps are poorly understood, I would say. What I put it here to some tectonic formation models they propose for them to explain. And I don't want to go much more detail, but just keep on your mind there's a red boxes. This is basically a straight fall model from Golombek. And these are the like SUPA model and the Chester and Chester model. It's called fault propagation fault models, and also different fault propagation fault models with the back thrust and the numeric models also used to explain their existence, why they are occur, and they try to adapt planetary information by using the terrestrial analogs also. Okay. The summary and the fundamental of this part is actually wrinkle ridges are basically fault propagation fault models and the continuum mechanical model approaches fitted for them. And both reverse and thrust faults can be seen for wrinkle ridges and with a back thrust implication. And different subsidiary and splay faults should exist because we can see them in the more wrinkly appearance. And it's thought to have form in a segmented because your thrust is shifting always, and we will see that in an example. And the lobate scarps are more straight, and the simple thrust fold models show the best match with them. And higher steep deep angles we have, like a reverse falls 45 to 60 degrees sometimes. And as I said previously, the flat hanging wall is a most unique indicator with higher vertical displacements. Okay, this was the fundamental part, what I would like to start. And the second part is the mapping. Of course, we are here for mapping. In the mapping part, we can do different kind of mappings. Like what you are doing so far in this week is geological mapping. But if you are a structural geologist and if you want to work on tectonics, you can use different approaches to understand the fault structures and fault patterns or underneath informations for these landforms. That's why I classify them the fault mapping by using the polyline. And after the crestline mapping, it's also polyline, but you should keep on your mind, it's only available for wrinkle ridges because in the lobate scarp we have flatten morphology, we can see any crest of the ridge, and geological mapping, but using the polygons, which is a little bit different than what Ricardo showed us like half an hour ago. And let's see. Okay, in the left, I put one of my favorite examples. We have approximately 5 kilometer wide wrinkle ridge intersects with impact craters. You should believe me, they're always fallen off. You can always find one wrinkle ridge and on top of them one impact crater, which is really useful because you need some subsurface information. And what I done over here is basically take some profile lines, what Ricardo showed us, to see how the symmetry, how the morphology looks like in the profile. In the A to A prime profile, we can see the symmetric wrinkle ridge, and the two sides of the ridge is approximately equal. When we come inside of the crater, we can see the one side of the crater highly uplifted. That means that ridge still continues to or postpone the formation of the crater. Another thing maybe you should keep on your mind, the size of the circularity of the crater. It's the right side, I mean, the east side and the west side of the crater is highly different. The west side is highly deformed. If you look and go into detail, by the way, these are the CTX images. You can see we mapped a lot of different lines over here. They should be not always the faults. We can call them the fault intersection lineations. They're likely the lineations seems like to be faults, in other words. And by mapping them, and after them, we can use the layering tool to measure the deep amounts and the azimuths also, how they look like. But it's not always easy because you can't easily see them. In this perspective, what you have to do, maybe it's also covered in this week, creating a 3D models, and on top of them putting these images and try to play them with the different illumination conditions and try to rotate them. In here, what we can see, apparently the faults are just how it's terminate, and we can see uplifted areas, and we can see inclined layers, and we also see over here how the fault is stopped directly. We can see the fault front over here, and so. This is another example for lobate scarp, as far as what I know and what I work on it. This is from the Mars. Here we see the flattened morphology. To understand that, what I did is like taking a profile line from A to A prime over here. And as I said, in the profile lines, you can see mostly the flattened hanging wall. And I follow the truss front and just measure that as a 67-degree angle of the dipping and the thrusting and so. Okay. By the way, I forgot to mention over here, when you're taking the elevation profile lines, it's really useful, but you always keep on your mind what kind of data you are using. That's sorry. Oops. That's the TTX DTM in the west part, and that's why I can see all the informations over here. But for example, if you are dealing with the positive relief structures, or maybe the riftings, maybe the collapse pits and lava tubes, whatever, you should always keep on your mind they are not like huge features. You should focus on more detailed way, and you consider your data. I plot that over here to show you from the differences between CTX DTM and the MOLA DEM. In the first day, Ricardo mentioned that we have the MOLA tracks, like the laser altimeter, and the points. And if you want to get information from the ridge crest line, for example, over here, you can follow this information over here because it's just a gap and it's just simple interpolation. And you can basically miss that part. Or if you want to have another information like the back side of the thrusting, like it's like a simple thrust, or is it like a 2-ram flat thrust, or fault band or fault propagation folding, these informations at least require high resolution data. Okay. And the crest line mapping, which is really important for us, because what we can do by using the crest line mapping, in the right side, what you can see is the beautiful wrinkle ridge, and the west side and the east side easily visible on the CTX image. What I done, I mapped all the crest line, basically of the wrinkle ridge, and I took the profiles perpendicular to the ridge. It's really useful for structural analysis, because you can see how the polarity of the ridge is changed, because where do you have the maximum displacement on the ridge, on the thrusting, that means you have the higher shortening, and that means your fold is actually there. And by following that, you can make a statistical analysis. You can write in a code for that, and after then plot them by the distance or by north to south, how it is changing, and you can compare to is there any kind of trend or anomalies, and etc. Okay, another stuff is geological mapping. The geological mapping is also really crucial and the main goal of this talk today. And geological mapping can be done for different aims, especially if you are dealing with tectonics. You can create tectonic stratigraphic maps. You can create like chronological stratigraphic maps, and etc., like the pure geological map. In this case, if you are dealing with wrinkle ridges or the lobate scarps, always consider the albedo. In the right side, we have TMS data, this infrared day image. I took the profile from A to B, and the upper part is the CTX DTM, and we can see some correlations between the CTX DTM with the TMS image, and where the slope is increasing, basically your TMS data would be increasing, because your sun-facing side of the ridge is exactly looking for the same side, and you can try to correlate that kind of data by using DTM and the TMS data together. Beside of that, the Ricardo covered all the part for me. Thank you. In the previous talk, you can use hill shades by using the hillshade, you can manipulate the illumination angle and try to look from different angles. And also you can create a slope map as you did for central peak of the crater and the moon. And you can also use the aspect map to defining the boundaries of the ridge, because we have to know where the ridge starts, we have to know where the ridge ends, and so.
Thanks a lot, Oguz.
Okay, that's my last slide. Actually, I would like to show one example. You put the Themis background, and after that you plot on the CTX DTM and the map by using the where it is ending. But it's not always true, because don't forget to check your color ramp. You have to minimize and maximize of your color ramp, and afterwards you are missing some parts like this over here. That's just the one experience problem during my learning, and you should take care and always try to correlate with the profile lines. For example, over here you have the offsets and you can find where it is starting, and so. Yeah, that's the final product. If you really want to go for the polygon, it has advantages and disadvantages. And I would like to say you can use for different purposes, like calculating shortening, area or volume. And you can just cut all the polygons afterwards to determine the polyo surface, or in another words, like more aesthetic view in the end of the map. Okay. Thanks for listening. That's the final verse. I don't want to take much more time. I'm a little bit 2 minutes left. And these are the sum ups. Like the most important part, only as good as the resolution of your data could be your observations. You should consider that. And different lighting conditions, slope and aspect maps, useful for boundaries. And elevation profiles always help with that. And don't forget, these features are complex, imperfectly understood, and we are still working on that, but very useful for different purposes also. Thank you.
Thanks a lot, Oguz. All questions will be on the Q&A or on Discord, and we move on to the next one, because today we are very packed with the schedule. Thanks again.
Sure. Bye-bye.